Modules 1 through 3 have focused on power electronics and the physics behind linear regulators, buck converters, and boost converters. In this module, we will introduce the control systems that govern these power converters. Module 3 includes a deep dive on the buck converter, which derived the output voltage being equal to the input voltage times the duty cycle. This implies that if your input voltage and output voltage stay fixed, the duty cycle of the buck converter should stay constant. In an ideal, lossless system, this is the case, but unfortunately power supply circuits are not lossless. The losses increase as more load current is pulled from the output, which in the case of a fixed duty cycle system will cause the output voltage to sag as load current increases and vice versa. To account for changes in load current, a control system needs to be implemented to adjust the duty cycle and regulate the output. A controller paired with negative feedback is used to do exactly that. The objective of control theory is to control the plant, in this case a buck converter circuit, so that its output follows a reference signal. A controller is designed to monitor the difference between the sensed output and the reference, which produces an error signal. This error signal is fed back to the controller, which adjusts the plant operation, in this case the duty cycle, to bring the sensed output closer to the reference. When applied properly, feedback will reduce or eliminate the steady state error, compensating for circuit losses at different load conditions by increasing or decreasing the duty cycle. Feedback will also reduce the sensitivity of the system to parameter changes, including variations in input voltage and load transients. It is used to stabilize the system and gives the power supply designer the ability to modify the gain and phase over frequency, which is critical in power converter compensation. Three main feedback control topologies are hysteretic mode, voltage mode, and current mode. All three are widely popular control methods in industry, and each offers unique benefits and trade-offs to a system. It is important to understand how each of these works to choose the best type for your application. We will take a closer look at each of these in the next few slides. Hysteretic control is commonly referred to as bang-bang control and can employ techniques such as constant on-time or constant off-time. It is by far the simplest control method and is inherently stable without compensation. The output voltage is monitored against a reference comparator, and a new pulse cycle is initiated when the output voltage reaches a lower threshold. The pulse terminates after a constant on-time, or when the output voltage reaches an upper threshold. Hysteretic control operates asynchronous to a clock, which is both an advantage and perhaps a limitation in system design. Because it is not clocked, the controller can respond immediately to a load step that drops the output voltage to the lower threshold. Voltage mode and current mode controllers must wait until the next clock cycle before issuing a response to the voltage deviation. Fast transient response helps limit the amount of expensive output capacitors needed at the output of the power supply. Despite the benefit of fast low transient response, some systems cannot handle a variable switching frequency power supply. Customers may have tight frequency spectrum windows for switching power supplies. If this is the case, then another control method that is synchronized to a clock should be explored. Other drawbacks include the need for sufficient output ripple for jitter and noise immunity. However, an artificial ramp can be easily implemented to solve this problem. And some of the original bang-bang controllers do not have protection against magnetic saturation. However, today's controllers employ quasi-fixed frequency operation and overcurrent protection, so this is becoming less of a concern. In summary, hysteretic control is a fine choice for power supplies that value ease of use and need extremely fast transient response. Care should be taken to understand the implications of a quasi-fixed frequency operation and its effects on the system downstream. Voltage mode control is a classic pulse width modulated control scheme that regulates the output voltage. It is very simple to understand its operation, but in practice, it is more challenging to implement due to the required loop compensation. Voltage mode control synchronizes the PWM to a clock signal. At the start of every clock cycle, the control switch is enabled, delivering energy to the inductor. The error signal, which is the compensated output voltage of the error amplifier, is compared to a fixed ramp voltage. When the ramp intersects the compensated error voltage, the controller disables the control switch. At this point, the control switch remains off until the next clock pulse. Because the ramp is simple and has a large magnitude, voltage mode control typically has better noise immunity than hysteretic and current mode control. However, challenges do exist with this control scheme. The inductor factors into the compensation network, which creates a double pole at low frequencies due to the LC filter. With ever-growing popularity of low-cost ceramic capacitors, the compensation exercise becomes tedious. In older voltage mode controllers, changes in input voltage affected the loop gain, making compensation even more difficult. However, now, more voltage mode controllers use input feed forward to keep the loop gain constant across line voltages. This must be considered when selecting a voltage mode controller. To summarize, voltage mode control is a widely used control scheme for power supply design. It is extremely good noise margin and a single feedback loop. However, the compensating task is less than trivial. The final control topology to be discussed is current mode control. Current mode is straightforward and resolves the compensation challenges of voltage mode, but it has drawbacks of its own. Current mode controllers are synchronized to a clock as in voltage mode control. At the start of every clock cycle, the control switch is enabled, delivering energy to the inductor. Current mode contains an air amplifier that compares the output to a reference, just like its voltage mode counterpart. However, current mode also measures the inductor current while the control switch is on. In this architecture, the PWM pulse halts when the sense current intersects the air amplifier voltage. This is different from voltage mode, where the PWM pulse ceases when the air amplifier voltage intersects a ramp waveform. One benefit of the aforementioned current mode architecture is it eliminates the inductor from the loop, providing a single pole transfer function that is a function of only the output capacitor and load resistance. Inherently, current limiting is easily achieved as the inductor current is already sampled. Peak current mode also simplifies the design challenges of interleaving multiple phases. There are a few drawbacks to this control. Most notably, noise from the switching transitions can corrupt the switch current sample and turn off the PWM too early. Controllers must address this through leading edge blanking or some other method. The controller also requires two feedback loops, a voltage signal and a current signal, which adds cost to the circuit. Lastly, a well-known limitation of current mode control is subharmonic oscillations that occur at duty cycles of 50% or higher. This issue is avoidable through slope compensation techniques, but it adds a layer of complexity to the design. Overall, current mode control is considered by some to be the most robust architecture due to its fixed frequency, parallelability, good transient response, and ease of compensation. However, the best control scheme depends on the system requirements, which should be carefully inspected before making a control decision. This concludes the fourth module on control theory and methodologies.